We were waiting on some people to show up. My name's Terry. I'm your maestro or master of ceremonies this morning, and basically a cat herder in IBM. I am a systems architect for our high-performance computing and high-performance data analytics team. And this is about the 11th stop on a multi-university tour we've been doing since about September. That started as a trial balloon at Georgia Tech in July. And so I have a number of colleagues with me here today, and we have a couple of subject matter experts on different topics, but wanted to share with you our team and what we're doing. Rather than get up and stand, since we got camera, actually people haven't talked to a remote camera before. So with me in the room, we have Dr. Jane Yu. She's on our life sciences solution architect team, and comes to us as a rocket scientist from MIT with an MD. So I'm proud to have somebody like that standing next to us that understands your problems. And then also to my left here is Stieg Klein. Stieg is a software-defined infrastructure specialist who specializes in what you guys know as GPFS, but today is called spectrum scale. I'll talk to you about that some more. And then the rest of the team is salespeople on the organization for covering the area here. Susie's out of the room. And in the back of the room, I have Ronak Shah. Ronak's our NVIDIA colleague. And so through the day, what we're going to do is give you a snippets of technology rundown that is in our high performance analytics portfolio today. It's my understanding, like a lot of places, that IBM's not been around for a while, and I don't know if that's the case here or not. Actually, you guys have a great reputation. I heard this is one of the top-notch HPC institutions in the United States. So that's the scuttlebutt anyway. So with that, a little bit of history about me. I worked for Hewlett-Packard for 25 years before I joined here in the enterprise space in Texas, with some of the largest HPC centers in oil and gas and seismic computing, so this is not an unfamiliar territory. But I joined IBM 4 years ago, and I was a chemist and computer scientist in my early career. A little funny story is, does anybody watch NCIS? Yeah, I was an Abby, the girl with the black tails running mass spectrometers, and then a computer scientist, so I became the geeky guy. And then I became an Oracle guy, and then infrastructure specialist. And I retired, and IBM said, "We want you to come talk." So that's what I'm doing. So here's some of the things we're going to talk about today, and these are the topics that I have in this all-encompassing deck. I got about 140 slides. I'll provide these back to your sponsor, probably David. And then you can distribute them. My request is they not end up on SlideShark. I don't want to see my name out there. This is between us and you, and keep it within the Indiana University community. Nothing proprietary here, but don't give it to our enemies and all that kind of stuff. So Jane is gonna give us a conversation about life sciences. It's in the reference architecture for that. I'm gonna take a poll here in a minute of what you guys are working on, so that we can calibrate our thoughts. Then I'm going to walk us through our storyboard about where we were and where we are now with servers. And then NVIDIA, we're going to spend some time in a little bit deeper dive with NVIDIA, and who's our major partner in deep learning and GPU space. If we have anybody interested in FPGAs, I'll give you a snippet of that. I understand there's an RFP out on the street for storage, so I have the ability to talk about it in general, but you got to tell me if I cross a line in terms of whatever the rules are on competitive bids out there. I'll share with you what our portfolio is, and you can go from there. We'll talk about lab services, our implementation team, open source databases, a little bit about OpenStack, and the bad word for infrastructure people called cloud. And we'll finish up. One of the things we've been having success doing is at the end, towards a couple hours from now, when we have lunch come in, we get in a corner and have two or three different caucuses with the subject matter experts. It worked out real well at Purdue yesterday. So with that, let me go into the next phase here. Actually, I want to take a poll from you guys. So I'm going to point you out, and I want you to give me 30 seconds or 15 seconds of what your niche is, what you're working on, because we want to understand how our problems can solve your problems or not, and we can focus our dialogues. Gary, you get to be first.
My name is Gary Motes. I work in the Center for Biological Research Collections. I do mostly biodiversity informatics, and so I'm looking at how fossil record and big data from biodiversity databases contribute to understanding of ecosystem modeling and health and forecasting.
All right, Dr. Jane's going to want to talk to you. I'll go this way. Okay. Any deep learning involved in that, in image recognition? Okay. So it's mostly data centric, not image processing. Okay. We're a TAC guy. Okay, I live in Houston. I'm 9 miles from TAC. Hope to be there in a couple of weeks talking to one of the TAC guys. We actually have, amongst that giant computer system, we have some systems there. Are you involved in C? Yeah. XSD? Yes. Yeah, so I'm going to talk to him about that. From our point of view. We can talk later. I have also, I forgot Michael, Dr. Michael Schwinn is our deep learning chief architect at IBM on the Watson Group. And so as we move into the deep learning topic here this morning, Michael's a smart guy and be able to tell you all about that. Mark just showed up. This is Mark West, our worldwide evangelist for high performance computing. I'm a new Mark, kind of. And so, good connect. You're the smartest dressed guy in here.
I'm a graduate student at the business school, studying business analytics
Business analytics,
and intelligence.
okay. Good. What statistical package?
Right now we're just beginning with R and using R Studio to R and then IBM has SPSS.
Okay, great. I have something I can talk about that.
I'm Dave Hancock. I'm the director of the school. Thank you guys for all coming down. All this is a reminder, the remote folks can only hear up there tonight. So if you have any questions or anything, make sure you take time to
For me, real quick, define where you have HPC and cloud merged together.
well, we have a work together kind of in practice.
Right.
Probably won't ever be for us. There's a lot of deals, a lot of good applications, different needs for use cases involved with thought leadership, DevOps philosophy, rather than traditional model, but we also have filtering codes that are going to run
I was at Clemson about a month ago, Dr. Mike Casey Lang. They, Clemson, Wisconsin, and Utah have OpenStack cloud shared
We can hear you not very well when you're standing there, and we can't hear the people out in the rest of the folks out there at all.
Okay. All right, I'll turn this around if I move around. All right.
And then just repeat their question.
Yeah, okay. That's what I heard.
Some introductions done to the manager here. So we have an HPSS archive system replicated. I got archive and then we have GPFS providing our home directory conduit storage, basically letting researchers get out of departmental files.
Yeah, they're asking me to do this. We did a tour of this event in Southern California, and I got pinged to go. I think I'm going to end up at Berkeley here pretty soon in a couple of months in March. So I'll see you there.
Hi, I'm Justin Peters. I'm with the Research Analytics team who support the discipline mathematical geospatial software on various systems.
Okay. So is that the statistics you talked
The
about?
software that he was speaking about, the SPS.
Or an SPS.
Yes, we deploy it and support it on the various systems.
All right. Are you guys a member of the IBM Academic Initiative? That's the free download of all the software, like SPSS.
Sure, we are. I'm sure.
I'm going to talk about it a little bit. Okay. Oh, that's Ian. Ian Watts is brand new to IBM. Ian is our new high-performance computing sales person for all markets. IBM's broken up into 5 markets: public, which is all state, local government, universities, healthcare, and then federal, Canada, industry, retail, financial services. And Ian's a veteran. We work together, and a seismic processing cluster expert from Texas. Sean, in the back for you guys here, Sean Cox is our storage rep, and I guess intimately involved in the open RFP, so we'll stay away from that. Yes. Yeah, I'm gonna talk about that. Yeah. That's right. That's right. Yeah, it's whatever Christy wants to. As far as I'm concerned, GPFS is whatever she wants to call it.
Spectrum scale is too expensive. We're just going to call you.
Yeah, right. Yeah, back. Okay. All right. Ross Caniglio in the back is our power system technical specialist. You guys, I think, know Eric from Logicalis in some way or another here. Who did I miss? Len in the back. Len's our power rep from, you're in Detroit? Okay. And I got everybody. Oh, Todd, did you want to say something on behalf of? Come up here.
One, you call it spectrum scale, Sean will give you better discount. And 2, I'm going to do a very formatted version of this since we have Mr. Mark West here. Mark made this a high priority to come in and say hello to you all. And there's one Mark West we have worldwide, so he's asked to go do some different things literally all over the world, specifically in HPC. He's done literally a bunch of stuff. But if y'all wouldn't mind, maybe have Mark come and do a little bit of a commercial, per se, around what we're doing in HPC, the strategy, what we're doing with this whole thing of open power, which you're going to continue to hear about, our partnerships, and all the rest of the good stuff, where we've been, where we're at now, and where we're going. But very lucky to have Mark here for our organization. I'm Todd Stacey. I work with this phenomenal team, Susie and Terry and the rest of the gang here. I'm responsible for all of our public sector U.S. strategic systems imperatives from a systems point of view. So all of our stuff supporting AI, cognitive, Watson, power, HPC, and spectrum scale, otherwise known as the higher priced GPFS version option, which obviously Sean's not doing a good enough job on marketing here. We'll talk about that later, Sean. I'm just joking. But give Sean a hard time, seriously. You get a discount, which apparently, y'all just need a new rep. Anyway, all right, guys. But thank y'all for having us. Mark, please. I got some.
Oh, yeah, I'll keep my comments brief so I don't take Terry's thunder. But, IBM is making great inroads with power technology, not just in HPC, but across the board. And 3 years ago, the Open Power Foundation was created, and that was coming together of IBM and Google and Mellanox and NVIDIA and a couple others that I can't ever quite remember. But there's almost 300. Last number I saw was 299 members now of the Open Power Foundation. You do have all my slides, don't you?
Right there.
So we're seeing, and where we're at now is we're seeing a lot of innovation and a lot of products coming to market out of those efforts of the broader open power community. So a lot of great things happening there. IBM, there was a slide that I just saw flash by. IBM is also obviously a leader in the cognitive space and now bringing that into the high performance computing space. So it's, I love this one phrase that, the fastest computing out there or the fastest simulation out there is the one that you don't do. And so getting smarter about picking what simulations you do, and if you can go and reap those types of benefits, you could have, 2, 3-fold. In fact, there's an example that we have of, it was 4 times less computation than we had to do, and we got 2 orders of magnitude better resolution of the output. And so there's huge movement there, and IBM with our leadership in the cognitive space is applying that. So those are some of the things that IBM's doing in HPC, and obviously continue to move our products forward. I'm not going to say much more because I know Terry will be.
Yeah.
So thanks, folks. I appreciate you all coming out today.
Yeah, Mark's our local Indianapolis team member. So with that, Mark basically took my setup slide, but that's okay. So what's happening here in this age, according from our vantage point, is that everybody's been doing HPC for quite a long time. This whole big data analytics world is growing rapidly, and what we're seeing is the merge or the confluence of data analysis, data analytics with high performance computing. We're actually calling that high performance data analytics, or HPA, depending on who you talk to. And in this world, we got to do things differently, and these are data-centric worlds. And so we're building our systems to map to this data-centric model. And in our giant IBM marketing process, that's the world of cognitive. Everybody hears about Watson. Watson is a cloud-based system or solution or knowledge engine, and what they don't know is it runs on the very computers that we're talking about today, that you can apply to your next generation. So and this is being done in oil and gas, research, as you know, material science, life sciences. The hottest topic in every one of these meetings we've done, this is number 11 or 12, is deep learning. And because of that, our advances we've had with NVIDIA, which we're going to talk about in a little bit, are leading the way in performance, and people don't know it because we haven't been out telling about it. And that's what we're doing. We're bringing this to you now. So in the world of social analytics, it's all about these type of graph analytics here. I actually have a customer doing in the South, doing homeland security, defense-related threat analysis with our power systems, and a software product that we don't have in our systems group, but something called I2, to take social media and in seconds determining the relationships between certain bad guys and other certain bad guys around the world. And they're being done on power systems because of the speed and agility of this stuff. Now that's a separate type of topic, but all these things are coming together. Okay, so we're working in these 5 areas. GPU accelerated databases, they're coming to the forefront. I'm going to talk a little bit about Kinetica and others. And And then in your world of universities and government research labs and whatnot, in genomics, it's the hottest topic that we see, with the most accelerated growth of data processing and data storage. And this is Jane's world of life sciences. She's going to talk about our reference architecture in a minute. And then, of course, high performance storage, which you're very familiar with. And I'm glad to hear you're an astute user of our system. And we'll see where that goes. And then the last one is deep learning with GPU-based neural network stuff. Okay, so with that, let me, I'm going to launch, you got to talk from up here, so we'll turn this down. So I'm going to launch Jane's deck here, and that's not right. Oh yeah, it's one slide off. That went to the end, sorry. We made a modification this morning, it took me to the wrong place. All right.
Okay, so I hope everyone can hear me. Those in the remote, am I good?
Yes, you are.
All right, great. So I'm Jane Yu, and I'm actually, as Terry introduced me, a computational scientist. So I didn't start off natively in IT, but my job as a computational scientist on the team is really to understand what your workloads are, what applications you're running, because at the end of the day, that's what our infrastructure has to support. And I'm going to be talking about some of the, one of the things I do is I travel to a lot of customers, very much like you, trying to understand what it is they're trying to run and what challenges they're having in managing, processing, storing, computing on big data. And I'm going to be, all of my slides have kind of a life science orientation, but a lot of the concepts that you're going to see in these slides really carry over to other types of computational science that involve big data. So it might have a life science orientation, but the concepts are pretty much the same. So what I'm going to be going through first is just a discussion of some of the major challenges that we hear about from our customers doing analytics on very big data sets. The first is very large data. And in the life sciences, we often encounter folks who are processing, analyzing genomics data, which is huge. Everyone sitting in this room has a genome that when it comes out of one of those machines, per person, 200 gigabytes. How do you make sense of that, right? So talking about big data, whether it's genomics, biomedical imaging, from either the laboratory or a hospital, electronic medical records, thousands and thousands of scientific articles that are published every day, time-varying sensors, machines, your Fitbits. How do you collect that data? How do you analyze it? How do you store it? All of this big data growing at a very, very rapid rate. How do you manage all of that? Okay, next slide. Okay, another problem that we see in academic research organizations, extremely siloed data. So if you're trying to gather all of the data that you need for analysis, it's often located in these different storage silos everywhere. How do you get that together in a way that you can analyze? And for even the top organizations we've met, they're doing a lot of this manually. They're doing it on spreadsheets. They spend 80% of their time cobbling together spreadsheets. So it's kind of saying, sorry, now what we'd like to see at IBM is that number in reverse. We spend 20% of the time cobbling together spreadsheets, 80% of the time actually doing real science. So we do our best to make sure that we actually capture or that is easy to analyze and automate that process.
Jane, I apologize to do this, but we can't hear you.
Oh,
you got to
sorry.
stand right.
Okay.
Sorry.
All right, so I'm going to have to stand here, I guess. So another thing that we deal with are very complex multi-step analytical workflows. The two that often come up with our customers in life sciences is genomic analysis, processing that 200 gigabytes of data that comes out of one of these sequencing machines for a single person. That workload itself, multi-step, can take about over 100 hours on a single compute node to process. We need to break that down, especially if we're trying to analyze 1,000 patients across a population. So incredibly important to cut down on the time it takes to process data, very complex data. And then a lot of large-scale text mining. This is also in the domain of our Watson group, Watson capabilities. So big, bottom line here, large, complex workflows that we need to manage. Right? Evolving frameworks. So the applications that our customers are using are changing all the time. Right, and so you'll see some of the applications we've run into quite a bit. You're probably using R, and I think there are some folks here who said they were using R. SPSS is one of the tools we have at IBM. We also have a lot of MATLAB, a lot of folks running the Python scripts. The two things that we often hear most about right now, Spark and Hadoop. A lot of any Spark users, Hadoop, okay. And then deep learning frameworks like TensorFlow, Caffe, Torch, Theano, all of these are really popping up. And not only are the different types of frameworks, application frameworks popping up, but there are different versions of those frameworks popping up. So we need to be able to support not only the different types of frameworks, but the different versions of those frameworks as they pop up. Databases are also evolving rapidly. We're seeing a real movement away from SQL, standard relational databases, into NoSQL databases. So common ones we see, HBase, MongoDB. We're also seeing a lot of graph databases, GPU-enabled databases, Blaze Graph, Kinetica, especially given the interest in deep learning. So we need to be able to accommodate all of that. Container technologies like Docker. I don't know if folks here are using containers, but there's a lot of interest in getting applications in a portable environment. So container, we need to be able to support things like Docker. Singularity, I think, is another one that we support. And then CUDA, which is a GPU-enabled platform. So the common thing to do with all of these different frameworks is to set up a silo, set up an individual cluster dedicated to that framework. We don't want to see that. We want to be able to run all of these frameworks on a common platform. It's a lot more cost effective, right?
I skipped one slide on here. Did we get this? Did we do this?
Oh, we did that one.
Okay.
Okay, another problem that we see, the world is getting smaller, right? A lot of your collaborators, if you're doing scientific collaborations, are living on the other side of the ocean. So what we need to be able to do is share that data, share those analytical workflows across remote distances. So these are things, and we need to be able to do that in a secure way. For healthcare, we need to be able to do that because a lot of that information is confidential, personal health information. How do we maintain the security of that? We have a lot of folks who are really concerned about their IP, their intellectual property. How do we safeguard that? So how do you move data, or how do you share data without compromising security on that data? So those are things that we need to address in our architecture. Okay, so when we go to customers, we see pretty much uniformly this set of 8 different requirements. First, scalable and low-cost high-performance compute and storage solutions. This data is growing extremely rapidly, and we need to be able to support that without causing a disruption within your data center, right? So we need to be able to scale up. Flexible architecture to support rapidly changing analytics applications and application requirements. Hadoop, Spark, different versions of Spark, TensorFlow, whatever you're running, we need to be able to support it, right, without disruption. Seamless integration of biomedical data or any other sort of big data on a common analytical platform. We don't want to be cobbling together spreadsheets. Rapid extraction and analysis of data, which is mostly unstructured. We see like 80% of the data in unstructured format, video, speech, natural language. So how do you take that data, process it, and extract, turn it into a format that you can actually analyze? Tools, metadata collection for repeatability and auditability for scientific research. You need to understand where that data came from, what has been done to that data, who touched that data, because you might be asked to repeat the analysis. Okay. You might be asked to repeat that analysis and validate it at some point. So we need to be able to collect everything about that analytical workflow that you would need to repeat that workflow at a later date, or find it within your storage systems. Tools for scientific collaboration, maintaining data privacy and security, and these are complex data centers. How do you manage these in an easy and cost-effective way? How do you reduce the burden for your IT administrator? Okay, so these are all requirements that we need to satisfy in order for our customers. Right?
We got you a mic to move around now.
Okay, got it. This is good.
It's on.
Is it on? Can you hear me?
Can you hear it back there, Tom and Indy?
Yeah, that's good.
Yeah, you can just raise your hand if I ask a question.
Okay. Can you hear me? Am I good?
Tom, can you hear her?
All right,
good.
All right, much better. All right, okay, next slide. All right, so what is our job within IBM systems? Well, all of us represent a group that is working to make sure that your systems meet the requirements that I just listed on the previous slide, and do so in a way that makes your workloads run quickly. You don't want your workloads to crash. You don't want your workloads to take forever to run, and you want them to run in a cost-effective way, okay, across the enterprise. And so we do that in a couple ways. We do that through acceleration at the level of the chip or the server, and we're going to be hearing a lot about that today with the work that's being done with Open Power and NVIDIA. And we also do that by creating an environment or software environment that allows us to use that work, run those jobs more effectively. Now, I'm actually going to skip this slide.
Let me ask a question of Christy and David, just for relevance. What scheduler do you guys predominantly use here?
We're typically using Moab, but we also have Worm and our OSG resources that we use.
So you got a little bit of everything,
We use all of everything.
right? Okay, I'll come back to that in my talk later.
Yeah, and
Okay.
actually, I'll stay with this slide.
Okay.
Instead of switching it. So essentially, what I mean by making better use of the resources you currently have, it goes to this problem of workload management. And this is sort of a conceptual depiction of what we're talking about here. So you can imagine each one of these colors represents a workload. On the y-axis, you see compute resources. So imagine each one of these being a server dedicated to a particular workload. What's plotted on the x-axis is time. And so you see at any point in time, you have some of your servers running. Now, in an inefficient system, essentially what you're going to be doing is running these workloads across time. You see a lot of white spaces here, and what those white spaces mean is that your job is not, those are idle servers. We don't like to see that. If you plot the utilization of your resources across time, you see a jagged profile. You don't want to see that. Essentially what it means is that there's a lot of waste in your system. You have idle servers there. With an intelligent workload orchestrator, essentially what you can do is kind of looks like a Tetris puzzle, right? You can take those workloads, you can, with knowledge of what servers are available, you can actually take those workloads and you make more use of what you have on within all the resources you currently have in your cluster. So what that effectively does is it reduces the processing time, okay? And when you reduce the processing time, it's great because you're making better use of what you've already paid for, and it reduces your need to actually build or buy more of your compute resources, all right? You're just using what you have now better. Okay, so, and we do this with a software layer, and I'm going to talk more about that next slide. So, okay, what do we do Well, here you are up here. Your users are up here. They're running R, MATLAB, Spark, Hadoop jobs, deep learning jobs. They're using a variety of different databases. You have your industry applications up there that, whatever it is, whether it's computational fluid dynamics or a genomic analysis workflow or some sort of complex simulation. You're running these on your compute servers, either x86 or obviously we're going to be talking a lot about power. Storage, you need to be able to store that data. We have, you can store it on flash, disk, and tape media, variety of media, and you can store it on-premise in physical clusters or in virtual environments like cloud environments. And we'll talk a little bit more about cloud later. But our goal is to make sure that those applications that you're running in the purple are running in the most cost-effective, time-efficient way on the resources you have, whether they're on-premise or in the cloud. And these green boxes here pretty much represent the different software layers that we use to make better use of what's down here. Right? Now, we're going to be spending a lot of time talking about power first. Okay? That's acceleration of that workload at the level of the chip and the server. Right? We'll also be talking about the workload orchestrator, which allows you to essentially do that Tetris puzzle a lot more effectively, make better use of your compute resources. When all these jobs are hitting your system at the same time, how do you allocate those jobs across your servers in a more cost-effective way? And enterprise data management, which is what you already have, your file system, your spectrum scale or GPFS, which allows you to access that data at low latency, allows you to store that data more cost effectively across different types of storage media, which gives you high throughput. All of those characteristics are created by our software. And we'll be going into detail on that next slide. Okay. Yep. Mm-hmm.
Well, I need to repeat the question. Yeah, so what Todd was challenging Jane was, Todd's our business development guy. What makes this unique in our perspective? Yeah.
So I work with a lot of customers doing healthcare and, projects in translational medicine, large-scale projects that are dedicated to understanding how to treat patients, diagnose, treat patients based on information in their DNA, what you've heard called personalized medicine or precision medicine. And what in my opinion, differentiates us is really our ability to understand end user workflow. We spend a lot of time working with computational scientists. It's not just an IT problem, it's actually understanding what workloads you're trying to run. And so we have teams of subject matter experts who will actually work with you to understand what your needs are from a research point of view. But we also work with IT groups to understand what you currently have in-house and how we can more effectively augment that. So it's not a matter of just buying a box. It's a matter of understanding how we're going to solve your problems today in a cost-effective way. All right. So in every architecture we propose to you will be based on your research need, your IT needs, what you have, and what makes sense for you financially. All right. So custom. It's not just turning on a power switch. these are complex systems, and we need to make sure we get it right. And so I think that's really the differentiator for us.
I'm going to add to that the word integrated, and I'll look at David and Christy again as the experts in the room. You guys are keen on GPFS. You didn't mention LSF. Before September, LSF cost a lot of money. I was in San Diego Supercompute Center in September, and I forget the lady's name who runs the schedulers there. And I said, what do you think about LSF? She said, it's absolutely fantastic, but it costs money, and we can't afford to spend our money on that. So we use Moab and Slurm and Torque, like you said. At the end of this presentation, I'm going to share with you how it is now part of the academic initiative. And it is integrated with GPFS to accommodate that Tetris puzzle we're talking about. And I'm going to throw out a challenge that you guys have the capability to help us integrate this and bring it even further into your world. So I'm throwing that out there as a challenge. We'll talk to you about an hour from now. Okay? Yeah, sure. Go closer so they can hear her.
Are we talking about changing behaviors of users, or is that the essence of it? You know, well, on the aspect of metadata collection, we've been to some really prestigious places where metadata collection is incredibly important, and they are having trouble getting their people to actually do it. And in fact, they keep metadata on spreadsheets on individual laptops, and then that person leaves the organization, and then it's gone, right? And that's typical behavior. It's typically what we see. We have this wonderful partner named Data Biology, and I have them listed up here. They've actually created software that automates the process of metadata collection. Lab 7 also does that. Whenever there's a niche that we can't fill for a particular requirement, I think Lab 7 and Data Biology are two of our good partners who specifically fulfill that need for the healthcare and life sciences space. We're going to partner with them. And Data Biology has been doing work with Genomics England. They do this type of thing at very large scale. We have, for example, other partners we have are Omisia, which that partner is important in the life science space, but essentially what they do is they do reporting on genome variants, genomic analysis. This goes through the labs. We don't have the capability to do that. We have some capability in the IBM Watson group. Everything up here, these are folks, a sample of folks that we work with in the industry to get these things to work, to meet the requirements of our customers. So we need some reporting capabilities on genomic variants. Omisia, big player in this space in healthcare and life sciences. We're going to partner with them.
Let me add to that a little bit, Christy. So Jane, I'm in Houston. We have MD Anderson Cancer Center there. Like you, they are an extreme user of GPFS with 7 petabytes of GPFS there. And we're actually our partners don't have to be vendors, they can be partners like you. In the case of MDA, Frank Lee, her predecessor, you guys probably know Frank, we're working on a metadata project with MD Anderson, which Frank calls the haystack of needles. And so all this genomic science data is composed in all these millions and billions of files. So with some, I'm going to not do good service to it, but think of a GPFS metadata crawler function that crawls all the files that are in this genome data, volume, or whatever, and goes back and puts metadata into the first bytes of those files. Now the next layer of this, I'm going to talk about prefetch with LSF in a later. So now the job can be smart by knowing where the files are that are relative to this patient or this genotype of a category of DNA samples, prefetch them to cache, and run out of flash cache our jobs. That's the kind of thing we're working on with a partner that is actually the customer. So it goes both ways. And you guys can take advantage of that too. Unfortunately, I don't know if you know about that because of DDN, because they wouldn't know about that, right? Go ahead.
Well, we're always interested in partnerships, whether they're commercial or academic. And as Terry mentioned, I mean, both of us are doing collaborations at LSU.
We're doing.
I have one at Imperial College London because this is a really tough space. A lot of the solutions don't exist yet. A lot of them are in development. And one of the things that we have at IBM is the ability to work with folks in software development to get these things to work. And we're happy to have, if there are any particular challenges that you have that you would like to have solved but can't quite find a solution for it, we have the ability to talk to our guys internally to see if we can actually get some sort of internal funding for some work on that particular project if we see a widespread need for it. So, I mean, that's one of the reasons why I work for IBM. It's having that access. So we can build sort of more leading edge solutions for folks.
How many petabytes of GPFS do you have here? 1 petabyte replicated? Okay. And how many files are underneath that? Yeah. I can give you an example of this genome work. One genome processing assembly produces 1 billion temporary 4K files. All of that has some piece of a metadata, right? And we're working on, Jane and I and Frank are working on projects on this at LSU, MD Anderson, and Baylor College of Medicine. So they're all in the south end, and that's extending up here to Chicago and other places. Keep going.
For domain-specific metadata, because having a GPFS or spectrum scale pro or whatever we want to call it would be able to add some technical attribution and other information. But for more domain-specific data, that kind of solution is not yet available across the board.
That's where we will bring in a partner who actually specializes in a particular domain. When you say domain, you're talking about industry or research field or that sort of thing, yeah. So, which is why the space I live in most of the time, in life sciences, we have Data Biology and Lab 7, who they're companies that grew out of the healthcare and life science field and laboratory information management systems. So
it's not limited to that either, though. We're not going to talk about it today, but there's things like Watson Text Analytics, where all of this data is in these books and archives and information. And with the capabilities we have with GPFS, you could conceive that a text analytics engine could crawl all these documents and create a metadata stack that's relevant, or crawl and understand what's inside doctor notes and bring that back to a metadata stack. So there's a lot that can be done with this. We're not Watson people, but Watson runs on the systems I'm going to be talking about. So there's a lot that can be done here, and the word partner could be you helping us do this. Yeah. Right. Yeah. Yeah. It's as much a practice problem as it is a data problem, right? The act of creating metadata.
Yeah, we try to automate that the best we can. One of the things that, actually, just back one slide, we understand that some of the expertise for these systems is not within IBM, which is, there are some really wonderful business partners who are just top-notch worldwide, like the ones up here. We consider IBM Watson kind of a business partner, or another division of IBM. But we take the best of what these guys have. And we're not arrogant to say that we can build it ourselves. I mean, we need to make sure that we give our customers the best that's out there, and which is why it's important for us to develop partnerships with domain experts. So we focus, within systems, we focus on everything in the green and the blue boxes. Spectrum computing, which is our workload management layer. Spectrum storage, and a lot of it built on Spectrum scale, or GPFS. And we'll be talking a lot about power, all right? So just to put into perspective all of the different products we'll be talking about today. And next slide, final slide, is we can do these systems on-premise or in the cloud. Imagine you're over here at Indiana University working on your application. We can send that workload. We can run it on-premise. We can run it on a cloud. We have SoftLayer, which is our IBM's cloud solution, but we also have connectors into AWS and Azure, if that's what you're using. And we can basically make this transfer of workload from cloud, from on-premise to cloud, back to on-premise, all seamless using Spectrum Scale, or GPFS, and our workload management software. But however you choose, the extent to which you use cloud, we have a lot. Are you guys interested in cloud?
David mentioned it. I didn't get the scope of it.
Yeah, I mean, it would take a lot of time to explain all of our content we do a lot of the enterprise side and different pieces of or in general looking for the appropriate resource for specific problems.
Yeah.
So there is a lot of interest in the cloud in the healthcare and life science industry. There are some reservations about using the cloud for protected health information reasons. That's the primary one. But this is where we would have a conversation, like to what extent do you want to use cloud? Do you want to do most of it on-premise and only part of it on cloud? What workloads do you want to run on the cloud? We can actually direct workloads to the cloud using policies. So, this is a conversation we would have. If you're interested in cloud, we can develop an architecture that meets the requirements that's specific to this organization.
Well, again, I want to take it one step further and say you can help us do this. I'm working at Skunkworks with Baylor College of Medicine. Baylor is the largest depositor of genome data into the Common Genome Repository at the University of Chicago. On the other end of that is our cloud object storage from IBM, but they don't have GPFS. So my project is to make that a seamless file system from one site to the other site. And I'm going to show you the picture of that a little bit later. Likewise, you guys have the capability here. You don't have LSF, but I'm going to share with you how it's free now, and you could jump into that, and you could be the creators or the testers or the debunkers of how integrated this can be, both local, LSF and GPFS, local and cloud. And so I see that as an area of collaboration that we can move into that's beneficial to all of us and the community. That's you? Okay. So with that, I'm going to spend some more time now moving through this world of compute nodes, storage, support, high-speed network. I presume you guys use InfiniBand? Yes? Yep. So I'm getting a lot of questions from, mostly in the healthcare space, where people have lost resources on their network team, and so people have said, okay, we have to get supported by our IT guys, so we're dealing with 40 gig Ethernet. But in general, our network system of choice is Mellanox InfiniBand. So I'm going to talk about all four of these things. Right now I'm going to move into the, oops, I got to go back to the top, get back on track because I had her slides at the bottom. Okay, let's talk about the system strategy. So here's the setup and the preface that the challenges that we've had over time for the last 20 years, people know and understand what Moore's Law was about, that over time the processor technology will go down in cost, and we will be able to get more and more out of computers, but we have reached a point of diminishing returns because there's only so much you can do with the physics of silicon and clock speed and other things, but the demand for technology and the use of those applications has created a gap, and that gap is being filled by everybody with accelerators, whether it's cache on a chip or firmware or FPGAs or GPUs. We have this big gap in demand of what the computer's asked to do versus what we can get out of some clock cycles. So that's on the left. On the right, as I just talked about, storage is exploding. I have a genome center that bought a petabyte of storage in Houston 6 months ago. They're buying 3 more right now because of these 200 gigabyte per person DNA files. And so this unstructured data and this explosion of big data is causing this storage growth process. So we have to do things differently. You can't keep buying more disk to solve the problem. So those two paradigms are coming together and converging right now. Okay. At the same time, in IBM, as you guys, I heard you guys have been with IBM all the way for high-performance computing all the way back since it was invented. So I don't need to tell you about our Series X platform, which I think you had, right? You had some here, Dave? Yep. So back in February of 2014, I think it was, the corporation decided to spin off the X Series business, primarily because we could not innovate something that we didn't have intellectual property in. All we could do was wrap sheet metal around it, do some electrical things, but at the end of the day, we didn't own an Intel chip. We couldn't provide innovation. So at the high level, the company decided that wasn't what we're going to do. We're going to innovate like we've done for 50 years. And we also realized that we couldn't do it alone. And Mark talked about this, but the story is that we said we got to do this with partners like you. And that was a complete turn IBM on its head of thinking, because before IBM used to be the company, this is before me, I just came here 4 years ago, so I can say this, that IBM used to be, we invented it, we own it, we are everything. Well, that doesn't work now. So, Open Power Foundation was formed to accelerate innovation, to provide capabilities, create an ecosystem of collaboration and reinvention and re-input back into the community. And the result of that is this picture. And 2 years ago, this was a relatively empty picture. Today, there's over 250. I have 3 pet projects on here. I did a little something for our buddies up in Ann Arbor 2 days ago. I made their Michigan logo spin. Is Indiana on here? I don't think it is, right? Yeah. So it costs nothing to join Open Power. And when you do, you are in with other organizations that are contributing back. And hopefully at the end of the day, we'll find some place where this is relevant. But Indiana is known for your prowess, and I would think you're a good place to be here. So my projects are with LSU and Auburn in cybersecurity. Baylor will soon be up here. And but we have software companies, we have systems integrators, we even have our competitors on here. And it's because our competitors are able to build systems with our power chip that fit into this community and take advantage of this. The obvious one is Penguin. So, and Mellanox, it started with Mellanox, IBM, NVIDIA, Rackspace, and Google, I believe. And today, Rackspace and Google have announced that 6 months ago that they are building next generation servers in the back that you don't know about, that you don't know you're using based on the power system, the open power box. So they're going to have their own box that's behind the walls at the other end of the Google Cloud. All that to say, it's an ecosystem of collaboration. Where we're spending our time in our high performance computing strategy is in these four places. We're totally devoted to OpenStack and bringing that to the forefront with you on the platform, whether it's orchestration and identity and network and storage. It is all Linux. On February of 2014, we had a major announcement besides Lenovo, and that was the fact we're going to support Little Indian. Prior to that, we had a rough road getting HPC of that generation because it was the opposite bit pattern of Intel systems, right? So today, everything we're talking about is Little Indian based. What runs on Intel in Red Hat Ubuntu SLS will run on this. So it's friendly now. Over on the compute side, we're dealing in our ecosystem at the mechanical level, the electrical level, firmware, etc. Certain vendors are writing firmware for us or firmware elements, add-ons, protocols, the interconnects. We're very tightly connected with Mellanox and NVIDIA. And I'll tell you about the example of our collaboration with NVIDIA around NVLink. We're going to spend a lot of time on that. So all this is about an ecosystem, not an IBM knows how to do everything all the time and you should buy it, right? Okay, you saw Jane's reference architecture. We're going to focus the rest of our conversation in the purple, blue, and green boxes, which is the software-defined infrastructure layer and the hardware layer. In our power system, we're working in these 6 areas, processor design. I meant to ask, is Indiana involved in the Department of Energy projects? So do you use Lawrence Livermore, Oak Ridge, or what's the third one, Mark? Argonne. Right. Do you have projects involved with them that are funded by them?
Not many. We have a few researchers with DOE awards, but most are great partners with NIH.
Okay. So you'll see why that's important in just a minute. So we're working with, at the processor interface level, we've got a technology called the Coherent Accelerator Processor Interface. So an FPGA, a Xilinx FPGA can see coherently all the memory in the processor. So the terabyte of memory on the processor is coherently accessible to the FPGA. And I meant to ask if anybody's doing FPGA work. In other meetings, we have lots of individual researchers. So that is a component of what NVLink is using. In the file system space, you know about GPFS. We have a storage system, and you are also users of HPSS. So you guys have been in our family for quite a long time. This is what I was talking about a minute ago. A year ago, about 18 months ago, when did we get award? When did IBM? November of 2014, IBM was awarded the $400 million project from the Department of Energy for the next generation of computing. And it was based on all the capabilities of NVIDIA and Power 9. We had to make a stepwise project to get there, but at the end of the day, 15,000 compute nodes at Lawrence Livermore and Oak Ridge are going to be replaced with 3,000 compute nodes, and I think it doubles the compute capacity while reducing by 2/3. So this is where all of our roads have led. It's based on Power 9. I'm going to show you a little bit in just a second. We had to have some interim stops. And so the universities that are doing work with the Department of Energy, everybody has, or the leaders have raised their hand in this meeting and said, well, It sounds like we need to be more aware of power systems and how they're working if we're going to be using those in our projects. And so that's starting the train of adoption. So we were not able to get all three departments because the government wouldn't allow one vendor to take the whole deal down. So Argonne is Argonne's next generation systems are based on an Intel platform. Okay. A few years ago, when we made this major transition, when we spun off to Lenovo, a few years ago, this chart was slim. Today, thousands of open source codes are ported to Power. People don't know this. There's more coming. I just got a new spreadsheet a couple of days ago. It's too thick to put on a slide, so this is irrelative. What we need to know as we're starting to communicate is what are the codes and workloads you're using so I can find the outliers. We have actually commissioned other universities through our academic initiative program and our university alliance to port codes. Oregon State University last year, the last year and a half, ported over 1,000 codes in the open source stack to Power. We have that option here, and we have porting and tuning people to help you do that. Okay. These are some of the computing packages available. We have a team right now at Stanford doing a porting process to Power to take advantage of what we're going to be talking about here in just a second. But it's not that difficult to do. In the Hadoop world, all the major Hadoop stack works. We take a little different stand on it. We're building appliances for Hadoop stack, and I'll talk about that in a minute. But this is all the Hadoop. It's all running on Red Hat. Everything is 7.2 plus meaning ongoing, Little Indian. And in the case of Hadoop, it takes advantage of one of our most significant capabilities, which is simultaneous multi-threading. I'm going to ask a question. How much of your workload here or code is hyper-threaded turned on in your Intel systems? And you've just given me the answer that everybody says. We don't use it because it doesn't work well. And what I can tell you is that SMT8, if you don't remember any other number, remember two numbers, 4 and 8. So the number 8 is 8 threads per core on a Power processor. Hadoop spins parallel with 8 threads per core, which is the yarns. I was personally a part of a project at LSU last year. We published a white paper. I'll share it with you, and I'll tell you the story of how we ran 9 times faster a workload on 40 nodes that took 120 nodes in Dell systems. So threads is that's all about threads in that case. a little bit more focused area. As an architect, I'm sitting down with customers to say, what are your workloads? What are you trying to accomplish? How does this system need to be built? And I'm working in an idea of rack level focus. At the compute level, all of our servers, here's the secret decoder. Secret decoder, S stands for scale out on the model number up on the top left. The 8 stands for Power 8. Mark, I presume 9 will be a 9, okay? The 2 stands for 2 processor. And the second 2 stands for 2U. So Power version, U space, processor, and U space. The LC stands for Linux cluster, or I call it the low-cost one, so that we can be back in the game with everybody else. The other half of this puzzle is GPU-centric. We're supporting 2 flavors of the GPUs, K80s from NVIDIA and the brand new P100. We were the first one to the market with the P100, which Ronak's going to talk about in a minute, using NVLink native with our significant advantage I'll show you. At the switch level, Mellanox InfiniBand and Ethernet switches. We have a lot of Mellanox InfiniBand and Ethernet switches for the high-speed network, and all of the servers today are IPMI-based management controls, so there's a 1 gig management layer underneath that. The parallel file system you know about very well. It's GPFS, spectrum scale, Sean, and we package the system up in a tuned, performance-optimized system called the Elastic Storage Server, which is probably what's in our response. I'm not sure. I haven't been part of that project. Okay, here's the meat of the server platform. In the center is what everything has a project name at IBM. The center box is called Minsky, so if you hear us say Minsky, that is the NVIDIA P100 GPU system with NVLink. I'm going to break down NVLink in a minute. 2 processors, 20 or 24 cores, 2 or 4 GPUs. Power 9 will bring us a 6 GPU version, and a terabyte of memory. On the right-hand side of the picture is our brand new 1U server. When we spun off to Lenovo, when we spun our x86 business, we lost our dense computer. We have an option back now. This is actually built by the one in the middle is built by an open power partner. The one on the right, 821LC, which the 1 stands for 1U, is built by Supermicro, the open power version of their server. And it's 2 Power 8 processors, has the capability. We can put K80s in here, right? Yeah, I think I didn't know that. Okay, so P100s are K80s in this system. And on the left side of the center is, actually that one's called Stratton, by the way. If you hear us say the word Stratton, I remember Stratton for small. The one on the left with this 12 disks in it is, our code word is called Briggs. Briggs is for big. And that's a Hadoopish, a big data server, 12 internal disks, 2U, 2 Power 8 processors, etc. The Briggs and Stratton servers have half the memory bandwidth than the one in the middle, so we have to characterize what your workload is and what's the memory and I/O bandwidth to put them in the right place. But if you're doing GPU work, the center box 822LC will be our answer to the solution. On the left is one of the servers we're using inside our Elastic Storage system. It's the predecessor to the 3 in the middle. And the right is commonly known Firestone, which is the K80-based GPU server. So those are our 5 server platforms. We got more coming in late 2017. For the Coral project, we have to deliver to the government 3,000. It's 3,000, right? We have to deliver a whole lot of servers to the government before we deliver to anybody else, and those will be the first Power 9 systems in the first quarter of 2018. And here's the Power 9 chip picture. I'm going to give you these slides. There's nothing, they're not confidential. This is the public information. So you can see we have a roadmap. Power 9 will bring more memory bandwidth, more cache, more reliability, and so that's what our next generation that the Coral project's based on. We had to go through an interim step to get there. So, Mark, you see what I did with your slide here? So, if you don't, these are the 3 things I want you to remember. This slide used to say 4x in each of those boxes. I changed it to 400%. But threads per core. If your workload is threadable or thread aware, then I want to challenge you to put it to the test with our system, and you'll find great results. Whether it's 4 or 8 remains to be seen. As I said earlier, Hadoop and the way it works is absolutely fantastic with 8 threads per core operating. We're finding that things like computational fluid dynamics are more memory intensive, and SMT4 is working more optimal than 8, but everything is workload dependent. That's kind of what we're trying to figure out at Stanford with one of their workloads. At the same time, 4 times more memory bandwidth between the processor and memory on our power system than Intel. And lastly, 4 times more cache. So when you put all 3 of these things together, that's what makes the system work and scream in this big data world. Left alone by themselves, it won't have the big impact. And so, think 4 and 8 in case of threads per core. On a rack level, I'm designing systems which you know more about than I do, but I'm thinking of in the concept of head rack, which contains login and management nodes and X amount of storage if storage isn't off by itself. And then and these login and management nodes are generally being built with 1U servers, which are economical and still have the performance needed for that function and with cost and space savings. On the right side, I'm trying to depict the integrated world. We are spending a whole lot of time integrating the servers and all the server capability that Jane was talking about with LSF to be resource aware. And so our platform is integrated together. Cluster Manager is actually XCAD on steroids. I don't know what you use for a cluster dispatch system to dispatch the OS. What tool are you guys using? Yeah, I've heard Cobbler a lot. Cluster Manager is the dispatcher, so the image, what's the right word? Pushing the images out as nodes change their state. It can be out of the picture and not affect anything else, but it's integrated with the system. The heart of our high performance computing software is LSF, load sharing facility. So again, I want to challenge you to see if we can find a place where you can be leaders and help us promote this and adopt it. LSF comes with 2 more layers, Process Manager and Application Center. These are represented by the graphical user interface. Today we have a lot of millennials coming in to learn what high performance computing is. They live in this graphical user interface world. We have today you can do that workload administration on your iPhone and your Android from the apartment. You can do real-time monitoring of the cluster on your iPhone or iPad from your apartment or work, wherever that is. If that's relevant, I don't know. But LSU a year ago saw this as a next generation, so they've adopted Process Manager and Application Center into their teaching process for new students on what is HPC about, and here's how you create a workload and a workflow. And they've taken it one step further, and I don't have their picture, but you can imagine that this is the workflow of an HPC job. Somewhere along the way in the if then else and activity state, they actually have created a step where it goes out to Watson in our Watson cloud, does text and content analytics, brings the data back to the cluster in Baton Rouge, and continues on in the job. And it's a great example of hybrid cloud teaching experience and understanding. So that's kind of software and hardware integrated together. Yes. 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 It's actually, yeah, so the question was, can LSF and I'm going to add words, and its mate software manage Hadoop and Spark jobs integrated? And the answer is yes. We're going to talk about that a little later. Stieg just stepped up because he's the expert on it. But in what you just asked, that fits into what we call our Conductor and Symphony platform, which are the orchestrators. LSF is underneath managing what job gets put on what node, at what time, with what data file. Conductor manages the orchestration of the jobs to LSF, okay? And we'll cover more about that. I'm actually slim on the slides on the material for Conductor and Symphony, but we can take that as a thing I'll get back to you, okay? All right. Yeah. Stieg is the expert on that. So here's the heart of our deep learning system and our GPU space. It's the hottest topic we've been talking about on this tour because of the secret sauce. I'm going to point to it right here. This Intel does not have, never will have. They have this, but they never will have this. And this is really important in this deep learning space, in the load time it takes to put, I think you were the guy talking about medical images or something? Right, so a lot of customers are doing image analysis of brain scans and breast cancer and whatnot and all these MRI scans. Well, that's large images. And those large images have to be put into the GPU to process. And that is the bottleneck. And so today, IBM, through our NVLink integrated with NVIDIA, can do 40 gigabytes per second bidirectional load into the GPU from CPU to GPU. It is very significant. And I'm going to show you some charts that talk about some real live numbers. At the same time, the processors talk to themselves across the 40 gigabytes per second internal bandwidth. So when you put all three of these things together, that's what's giving us our 3, 5, 10x performance gains over everything on Intel, including 5. Okay, so on the other side of the equation is regular dense compute nodes. One use space, lots of nodes, smaller memory footprint, not as much need for deep learning. And this represents 4 racks of one-use servers. The power envelope for the electrical, we can put about 32 in a box in a rack before we start running out of people's ability to supply power to it. Each server is only 700 watts, but in general, most data centers are telling me that they can support about 35 kilowatts per rack, something in there. What's your data floor power capability? How many? What's your ceiling of kilowatts per rack? Okay. Okay. We get asked about water cooling too. What we're finding is that the performance we're getting out of these new systems is alleviating the need for water cooling that Intel has to have. So in general, I was trying to say that I'm trying to build to about 35 kilowatts per rack. Okay, so a little bit more about NVLink. NVLink is between the CPU and the GPU. It's the fastest bus bandwidth. And the significant part, again, is the link between the GPU and the CPU. We brought these out September 30th. We had to ship the first 200 to the government. And we sold out within 2 weeks. To characterize that with Intel, on the right-hand side of the picture is the x86 version. You can buy a P100 GPU from Ronak, from NVIDIA right now, and it will be PCI based. Intel will never have NVLink to the processor, and those GPUs are communicating at max 32 gigs a second, but the bottleneck in this deep learning world is from the CPU to the GPU. So this is where this 80 gigabytes a second is coming into play, and we're seeing in aggregate all the workloads are performing in GPU speed 2.5 times plus more than this equivalent Intel. So because these systems are in demand, and we don't have a good ability to get one out to everybody that wants to have one, which is everybody. We have an NVIDIA acceleration lab in Poughkeepsie, New York. We have 50 nodes in a cluster up there with Mellanox InfiniBand EDR and back-end petabyte of GPFS storage. And so if you are a researcher and you have a high GPU workload and you say, I want to understand this, then myself and my colleagues, we can create a queue request, and we can give you for a month or whatever the project entails. We have to write a project plan. We can give you a queue to use those remotely. And we have just got done in December with Princeton, Virginia Tech, Southern California, LSU, some others. These are the ones I was involved in, all using these systems. And every one of them, when they come out of their project, we're immediately having a dialogue about a rack of servers to be deployed into their environment. So I throw out another challenge. We don't have as many researchers in the room here, but I throw out another challenge. Give me your hardest workload that is GPU-centric, and I'll get you in our lab, and we'll put it to the test, and I'll buy you a steak dinner if it ain't better than what you're seeing right now. So that's the least I can do. So somebody always raises their hand. I've got one, let's try it out, and we want to do that. Short of that, it's very hard to bring them to the table, but that's the job of the sales team to figure out how to get one here if you have an application you want to try. In the lab, we have tuners for Linux. We have tuners for CUDA. These run on CUDA 8. How much CUDA coding do you guys do?
I think we have some, almost 700 GPUs with one
CUDA 7. Okay. So I didn't ask this question at the beginning. How many total compute nodes do you have across all your clusters, Cray, and everything? A couple thousand. So how much of that is, what's the percentage of GPU? A third, right. I'm generally getting 30% GPU-based, 70% compute-based. So that's right in line. So what we're not naive enough to know that we can't come here and say, hey, change everything out you've got for IBM because we're the greatest in the world. But we believe that we have the right answer for the GPU space for that 30% to move to, and we want to put the test. LSU, I'm going to show you a chart later, but a deep learning chart that they just published. They're publishing, it was based on all NVIDIA GPU comparisons. The next one coming out is against Phi, and it's amazing. Okay, so at this point, Ronak, are you going to do what Brad did yesterday? Yeah. Okay. I gotta drop out here, get to a file I forgot to load. Well, and Ronak, here's your microphone. Do I need this? That's for the people in the okay. Gives you the ability to communicate 200 miles. Yeah. Okay, let me go find that guy. Hold on. Go ahead and dance. You get to dance right now.
Yeah. Well, good morning, everyone. My name is Ronak. I live in Chicago, and I'm responsible for our research computing relationships within the Midwest. So pleasure to be here.
I forgot.
So I'll go ahead and start talking about kind of NVIDIA, give you a quick background on who we are. We were founded in 1993 by our founder and CEO, which is rare in the Silicon Valley to have a founder and CEO of a company that's worth $60 billion. The main reason why we were founded was at the time our founder realized that CPUs are not able to render graphics, right? Because if you look at graphics and what it takes to shade and render, the most minimalist component, essentially the atom of graphics, comes down to performing calculations on triangles, and lots of them in parallel. And at the time, there were really not that many technologies out there to perform all these calculations in parallel. So he created what's called a parallel architecture, and fast forward 5 years, what we did is we took that architecture and we layered 13 million lines of code on it to create a supercomputing platform. And what that did is it's able to execute CUDA, which is our programming language.
Catch you on slide 1.
All right. What it enabled the GPU to do is execute our programming language known as CUDA. And along with that, we released a bunch of libraries and SDKs, and that enabled the GPU to become what's known as the GPGPU, the general purpose GPU. And that's what the Cray system over here on campus, the Big Red 2, is adapted as our Tesla product line. That's easily programmable. It can run any instruction set from within the CUDA parameters. So next slide. AI is revolutionizing HPC, and we have a lot of examples of where deep learning has been utilized, especially in the public markets and the government. A good example that we use is NASA. NASA's created a deep learning framework known as DeepSat to look at satellite imagery and help crop production and look at greenhouse emissions and the carbon footprint. Another good example coming out of NASA is the deflector selector. And that's based on GPUs as well. And that's a technology that predicts with 98% accuracy which technology is able to deter the Earth from having asteroid collision. So there's a lot of different ways that our government as well as higher education institutions are leveraging deep learning today. And this is one good poll right here that we took at Inside HPC. 92% of HPC users say that AI will be impacting their work in the future. And what's most interesting is 93% say that deep learning is impacting their work today, right? So not even in the future, it is impacting their work today. Next slide. AI is definitely built on HPC. The AI workloads require, it's basically, if you look at deep learning, it's a lot of dense linear algebra, right? It's a lot of matrix on matrix multiplications happening in parallel, and that's where GPUs are most suitable. And once we figured out that there's this massive trend in deep learning about 5 years ago, we started investing a lot of our time and effort into engineering a deep learning-based solution. And one of the things that we're very proud of is having 1,000 engineers out of the 2,000 GPU engineers that we have right now dedicated to doing engineering and innovation work on deep learning. And for that reason, we've introduced the Pascal P100. We've rolled out a couple different SDKs and libraries. And also, we've introduced a lot of these frameworks, our own framework known as NVCafe. We've accelerated all the different the frameworks on market, Cafe, Theano, TensorFlow, all of the major frameworks are right now GPU accelerators, so they can leverage the compute capability of a GPU and multi-GPU systems. This is a cool slide because it shows kind of how data is growing. Yes? Yes. You know, that's actually a great question for Mike because, and I'll.
Mike's, we're going to hand off to Mike in a few minutes. He's our chief architect, so hold that thought.
This is a really cool slide because it shows kind of how much data there is in the world right now and how it keeps growing. And if you think about data, data doesn't really get lost. You know, people retain data, organizations retain data, users retain data, and with the amount of sensors that are growing in the world for creating data, the data just keeps growing. However, up until now, up until the past probably 5 years, we weren't able to use the data in a cognitive way, right? So if you look at what's happening in the analytics world, for example, there's an oil and gas company in Houston that uses 30 years of seismic data to do deep ocean exploring. Before they were doing that, they had to go out and do a lot of exploration and testing to figure out where to drill and where they can get the oil. However, with the data that they have on hand today and GPU acceleration, they're able to use 30 years of seismic data to predict where they're most likely to find oil. So there's a lot of examples out there how even using data and GPU acceleration can lead to results and insight from that data. The three pillars that we practice and on our AI philosophy, it comes down to these three pillars. Being able to analyze what's in the data, and that comes from a lot of our partners like MapD, Kinetica, that use GPU accelerated in-memory databases. Visualization, there's no doubt about it. When you have a lot of data, it's the easiest way of recognizing patterns from there is organizing and presenting them in chart formats. Visualization is something that we've perfected for years. We're hardly, we're, I would say, arguably the best graphics company that's out there. We have 50 to 60 million active users on our gaming platforms. We've created and invented the modern GPU, so this is a space that we excel in. And the third is actually what's most important today is AI and acceleration, right? If you look at analytics, AI has existed for 30 to 40 years, right? The most primitive form of AI has been algorithms. However, with deep learning now, we've been able. Does anybody know about deep learning, by the way? What it is at a high level?
I think this guy in the back.
You know what deep learning is. Okay, so deep learning at a very high level is basically the philosophy of scientists realize that we're having a hard time getting computers to learn and act like human beings. It was all algorithm based. And scientists figured out how can we train a computer to think like a human being. And they studied the human mind, and they took the way the neural pathways work and the way information works and the way our mind is trained and the way the information flows through a mesh of networks and a matrix and outputs a result. And they modeled a network based in the computer to train it and actually do inference and training and be able to predict outcomes. So that's what deep learning is. It's kind of what you see over here, this matrix. That's a deep neural. That's not really a deep neural network. It could be a deep neural network, but it looks just like that. Analytics and use case. Yes. So this is actually a really cool side because up until 10 years ago, we had no customers, right, in terms of selling direct to an end user. Most of our customers were OEMs. There were gaming companies, consumers, and what have you. But now with our AI capabilities, we're talking to everybody. Automotive, Tesla's new autonomous vehicle is going to be based on our Pascal P100 that I'm going to be talking about. Consumer packaged goods, we're doing a lot of robotics and manufacturing and predictive maintenance, financial services. There's a lot of hedge funds out there that are using accelerated financial packages that are doing a lot of computational finance. And all of these different industries. I mean, if you look at Facebook, and when you go on Facebook and it recognizes your picture and where it says, would you like to tag yourself, that's based on our engine. When you go to Netflix and it recommends something, that's based on our engine. Every single cloud provider uses NVIDIA acceleration. And the cool part about this is in education, right now, analytics is being used to predict student outcomes and look at students' data and predict which student is more likely to fail or drop out, and so that way the university can act on it. So analytics is used in every single industry, every single application, and I think we're going to see a massive growth in that as well. So this is our baby, and something that we're very proud of. It's called the Pascal P100. Right now in Big Red 2, you guys have K20s, right? Is that correct? And that was our Kepler generation GPU, and after that we had our Maxwell generation. So this is our second generation after that, known as Pascal generation. And the reason why we're so proud of it is because nobody's ever made in the Silicon Valley these many changes to design from a chip design perspective and introduce it with on time and on success and it being a colossal success. It was a whole new silicon manufacturing process. We introduced a new interconnect that Terry talked about, where you can connect multiple GPUs at 80 gigabits per second compared to 32 on PCIe. We introduced a new memory chip, unified memory, so that the actual memory is on the chip. So if you look at these four stacks right here, these are the actual memory stacks on the chip. So you no longer have to move the memory from the chip onto the motherboard and back and forth. We've introduced line level coherency in lieu of page level coherency. So we've had a 100-bit bus that's gone up to 4,096 bits. From a performance perspective, it's about 2.5 times faster than the K20s on double precision, 3 times faster on single precision, and at half precision, it can do 21 trillion operations per second. So this is what Tesla's new autonomous car is based on. This is what's in the trunk. It's 225 watts to get 21 teraflops of performance, half precision. So this is just a beast.
The things that we are collaborating with NVIDIA on is the second and the fourth box. Obviously, NVLink I've talked about, but through CUDA 8 and the libraries with that, we and our coherent accelerator processor interface technology, CUDA and the GPU are able to see the memory of the processor, so that further reduces the load time and interaction time. And that's those two things are gaining us our giant steps forward with our performance characteristics in GPU space.
These are just some performance charts, how much performance we're getting out of 8 P100s connected together versus 4 versus 2, all compared to Intel Haswell. This is a cool chart in showing what GPU acceleration is doing to the overall software and hardware market. In the traditional sense, we've had the visualization companies like Tableau, and if any of these logos if you recognize them, the rise is because of GPU acceleration. And prior to GPU acceleration, we've had these core sets of technologies that have dominated the market, but introducing GPU acceleration has taken companies like Tableau and put a lot of competition on them, and introducing companies like MapD, Graphistry, BlazeGraph. There's a lot of in-memory database companies out there that are replacing the traditional database companies like Oracle and SAP. And the reason behind that is you can actually do the analytics as well as host the database in the same memory, and instead of having two discrete processes, and get real-time analytics. So there's a lot of different cool technologies out there. A good example of IBM being in there is IBM divested from their x86 business, and they recognized that in order to differentiate themselves, they're going to have to accelerate, and they were actually one of our first partners to adopt NVLink and our Pascal technology. These are some cool numbers of what the partners are seeing in terms of acceleration because of our massively parallel architecture. And one of the reasons why they're seeing this is traditionally, CPUs have dominated the market with linear code, and CPU chips have not gotten faster in over a decade. CPU chips keep getting wider, but not thicker, so multi-threading, a lot of cores. So once developers have stopped, or started adopting parallelism in the code, they've recognized that there's actually a greater use of GPUs once they start looking at parallelism. And this is what we're seeing. This is also another graph showing that. So I'm going to let Mike talk about deep learning and the Power AI.
What we're doing is, because I've been talking on a theme of integration and packaging. Mike's the head of our Power AI, or artificial intelligence offering team. And what we've done, I'm taking a little bit of spin, is to take the common frameworks and put them together in a package that works when we deliver it, and you don't have to go meddle with it. With that, go ahead, Mike. Oh, let me go one more slide.
All right. So when we looked at the landscape of emerging technologies that were going to change the industry, that were going to be a game changer, we recognized that this was the time for cognitive computing. You've heard our CEO, Ginny Rometty, talk about cognitive computing. IBM is calling this the cognitive era. When we look at the core technologies, what this boils down to is machine learning and deep learning, the technologies that allow application users, developers, to architect solutions that extract information from data, that harness these huge data stores that we just talked about, and extract information to learn from them. So this is a rapidly emerging field. It's very new, and all the applications in this space are coming out of academic and industrial research labs. Consequently, if you think about it, they're very new applications, constantly in flux, and quite difficult to build. The primary value proposition of these applications today to the developers is not that they're nicely curated, easy to build, but rather that they allow to make technological progress. So this is great if you want to develop new deep learning algorithms, but if you want to use the applications, that's a challenge because you don't want to spend your time building software that hasn't been curated for being easy to build and easy to deploy. So that's where we stepped in. We decided to build a software distribution for AI, for machine learning, for deep learning, by taking those packages coming out of industrial and academic research labs, curating them, packaging them up, building them so they're easy to deploy, and then add our own enhancements to, on the one hand, take advantage of the power technologies that we talked about, Power8, NVLink, the GPU acceleration, also algorithms that our own research labs in Yorktown Heights and then research labs around the world have been creating, and package all of that up. So take the public deep learning frameworks, add new algorithmic techniques and optimizations, and release them as Power AI, as IBM versions of deep learning frameworks that are easy to deploy, easy to use, that offer better performance. So, next chart, please. So with that, we've released a package of precompiled major deep learning frameworks, and you can install those on your favorite Linux with the standard system install commands, single command. You have all the deep learning frameworks installed on your system. And out of the box, they support all power systems with GPU acceleration. They're particularly optimized for taking advantage of NVLink and are enabled by our high-performance computing infrastructure. So let's go to the next chart. Today, Power AI includes Caffe, Torch, three versions of Caffe. The Berkeley Caffe, the original Caffe, NVIDIA optimized version of Caffe that NVIDIA is maintaining, and a new version that we call IBM Caffe with additional algorithmic enhancements that have been developed in our research labs. Torch, TensorFlow, which is rapidly gaining traction. That's Google's deep learning framework. They first released it about a year and a half ago. We partnered with them from the get-go to bring it to Power, to enhance it from Power, to take advantage of NVLink. Today, we're actually releasing a new version of TensorFlow, and there's going to be additional announcements during the day around our collaboration with Google to bring TensorFlow to the enterprise. Theano, another framework. We've also integrated Digits, which is a graphical user interface to simplify deep learning tasks, training of neural networks, and broad range of high-performance libraries, BLAST libraries in particular. We've worked with the open source community to optimize both OpenBLAST and Atlas for Power. We've brought Nickel, if you want to think of it as MPI for GPUs, that NVIDIA developed to Power. We've built Bazel, the build tool that is used in conjunction with models for Google's TensorFlow, neural network models for TensorFlow, and a host of other ecosystem optimizations to provide a robust technology base for deep learning, machine learning tasks. That allows you to take advantage of NVLink servers. It links directly into our high-speed file systems. Again, what you're doing with these applications is consume lots and lots of data to train, to extract information, to recognize patterns, and to harness those patterns that are recognized for applications for predictive or prescriptive analytics, for example, and scale that to the cloud. We've brought the NVIDIA Docker extensions to support GPUs within Docker containers to Power. So you can deploy containers with Power AI, with GPU accelerated applications, just like any other containers, and take advantage of the acceleration. So here is a detailed overview of what's in Power AI today. It's running on Ubuntu 16.04, which is the launch operating system for our Minsky platform with CUDA 8 and the latest version of CUDNN 5.1. We've worked with our Toronto software lab to get them to release the mathematical acceleration subsystem for Linux, which is a high-performance mathematics library, to integrate that as a part of the Power AI distribution. I mentioned already we worked with the open source community to enhance BLAST, the linear algebra package for Power, to take advantage of all the enhancements we have in the SIMD and the vector architecture on Power. And the 3 versions of Caffe, the digits GUI for Caffe, Torch, Theano. Today, we are officially announcing and making available TensorFlow 0.12, which is the latest version of TensorFlow. It's optimized for the Minsky system, but will run on any GPU-accelerated Power system and can take either advantage of PCIe-attached GPUs. So if you have a Firestone or some other one of our other servers for Power 8 servers with GPUs, you can use the same software there. All right. So what does what do we get from Power AI in terms of performance, in terms of performance advantage? So we have here 2 comparisons between a system running IBM's Minsky server with the P100s compared to an Intel server. The first one compares 4 GPU Intel system with a 4 GPU Minsky. And what we're seeing here is over 2.2x acceleration of the AlexNet neural network training process. So that's quite significant. And next chart, I'll discuss how we got there. No, let's stay.
Stay there?
Yeah. There are systems out there today that have 8 GPUs. If you look, for example, at Facebook, which released which showcased 8 GPU training server, a 8 GPU deep learning server. And so we also compared our 4 GPU Minsky system with what you can get with the 8 GPU PCIe attached Intel server. And compared to an 8 GPU server, we're showing an acceleration of still 24%. So our 4 GPU system is faster than the 8 GPU Intel system that Facebook and others have been using as their state-of-the-art system. Beyond the percent or 2x acceleration, the other thing I'd like to point out is as the key advantage that using these Minsky servers and the trajectory that we've had in terms of performance gives us is that when we started out on this journey about a year and a half ago, it took several days to train a neural network to do the image recognition for a ImageNet database, one of the sort of industry standard benchmarks. And today we can do that in under an hour. And what that does is it fundamentally changes the game of how you can develop applications, because the deep learning process, the neural network definition process, becomes interactive, and it allows developers to explore the design space, to try ideas, to get the feedback within an hour, and modify their suggested network architecture, to modify their setup, and try different alternatives. And that allows them to become much more efficient, discover better solutions. So it changes the game qualitatively, not just as in terms of having a speed up, but allowing you to do more, explore the design space, come up with better solutions. So if we're going to the next chart, I promise I'll highlight how we get the performance enhancements that I showed in the previous chart, what we're achieving with the NVLink attach. So this one shows a comparison of a training task for the ImageNet data set on AlexNet, one of the first deep learning neural networks that became notable most importantly because AlexNet was the first winner of the neural network-based winner of the ImageNet competition. So when you run that on x86, you see that there's a lot of time spent in transferring the data to the GPUs and to communicate between GPUs. And so in terms, compare that to a Power 8 Minsky system. In terms of compute, the compute is somewhat accelerated, but the most noteworthy difference that you'll see is how much faster, how much more compact the data transfer is. So the data transfer and the computation are much more balanced. You don't have these periods where the GPUs are idle while they're waiting for data here and again here. And so that overall leads to significant improvement in performance. For this training task here, we're going from 170 milliseconds to 78 milliseconds, so more than a 2x speed up. So if you want to try Power AI today, it's available for download from our website, ibm.biz/PowerAI. It's free of charge. It comes as a prepackaged Debian package, so you download that with a single command. You can install it on your system. It will work, as I mentioned, either on a Minsky server or any other power system with GPUs. If you don't have a GPU-based power system today, we have a cloud-based solution with our partner Nimbix. They have a container cloud running on Power Minsky servers. And so you can go to their website and rent instances. I think it's about $10 for an hour. So, and they have the same Power AI package in a Docker container running on their Jarvis platform with Power 8 and the P100s today. So Debian, yes, it's.
So that's the end of our Power AI talk, and it's 11:05. As you saw, I had to go to the bathroom, so I figure everybody else does too. We can take a 5-minute break here or so, and I'll blow the whistle, and we'll come back and move more into the workload orchestration and storage and networking categories of topic if you want to do that. Yeah, the gentleman in the back had asked a question, Mike. You guys can... Okay, we're going to get started. Hello, let's sit back down.
I'm happy to get you the background, but I would caution against putting it into the presentation because many of these guys are the application guys. They don't care. They just want to give it to somebody.
I understand. Okay, we'll talk some more.
Okay.
Now that you know how the flow works. Now you know how the flow works.
Yes. I don't want to. You got 180 slides. I hate to see it go to 240.
I want 3. All right, 5, 4, 3, 2, 1. Me. It always happens. When you break for coffee or bathroom, you lose half the audience. So the important people stick around. All right, so in right, so we've been talking about deep learning. I'm personally involved in a couple of projects. This was a little hot chart I got in right before Supercompute from my customer at LSU who's doing this very work. And I just throw it up here as an example of their proof, not my proof. There's a student at LSU who's doing his PhD in deep learning on these systems. And over the course of a week in our NVIDIA Acceleration Lab, because they didn't have one of these servers yet, he took an AlexNet deep learning algorithm and a breast cancer image file and did an experiment with forward and backward TensorFlow deep learning, what's the next word? I don't know the next word. Training, and then characterize the result on our IBM system over here, and all of their associated GPU-based systems on Dell servers in their multi-thousand node cluster at LSU. The net result of the same exact workload running across those systems was that the results of the IBM system was near 10 times better than the best one on the K40, I think it was, right? So it's just evidence of real world work that's exemplifying this. The next project, which I saw the paper last week, is that all these bars on the left are phi based, and it is 3 to 5x performance over anything they're seeing with phi. So again, proof in the pudding, but everybody has a different pudding, and so I challenge you to take your hardest workload that you have and work with us in our remote lab and see if you get to the same place as evidence. I got to catch back up because we had slides duplicated in different places. One of the things that we're seeing is that, I mentioned it earlier, computational fluid dynamics is very popular, but not as high performing with SMT8 as it is with SMT4, but in all cases, our Power 8 systems are performing tremendously better than the Intel systems. But again, the proof is in the pudding, and different workloads operate differently, so everything has to be characterized in its own context. Okay, let me talk about Hadoop and Spark a little bit. I saw we asked earlier, I forgot who was a Hadoop person. Nobody. Okay. You? Okay. So Hadoop is obviously the big data platform. Because Hadoop is able to take advantage of all these three major things I've been talking about: threads, cache, and bandwidth. And this was unknown to Hortonworks. It is creating tremendous shift in the way they're thinking. We created at IBM in the context of appliance. I don't want to use the word appliance. We'll call it purpose-built systems, where we take all of the components, we optimize them, we fine-tune them to deliver a system, not just parts. And so our system for Hadoop is called the IBM Data Engine for Spark and Hadoop. I got to reverse that, Hadoop and Spark, IDEHS. And what we're seeing is that we're getting upwards of 2 times better performance in the same set of node count as you would with an Intel system. We package them. There are 2 distributions that we're working with. I got lots of university customers that say, well, we don't want to use a distribution. We just want to use all the Apache parts and we'll put it together. But in the commercial space, where you have a company that can't afford to have their analytics run on an open source platform, they need a distribution-based platform like Red Hat is for Linux. Then there are 2 prominent ones in the market. The number one in the market is Hortonworks. And up until last fall, Hortonworks didn't play with IBM, but now they do, because they've, we did a lot of work to convince them. And I'll show, and so Hortonworks is supported on the power systems starting in March, I think. March, April, something like that. We also have our own offering at IBM from my colleagues at the software group. IBM, I don't know if people know, but IBM is the 2nd largest software vendor in the world with over 250 platforms of software. One of those platforms is called Big Insights. Big Insights is our distribution of Hadoop and all the elements, and it runs on both x86 and power systems. The power systems outperform the x86 systems in that venue too. So we're building these appliances in this kind of model, small, medium, and large. Now, if it doesn't fit quite right, we start with whatever the small, medium, large model is, and we take a few nodes out or put a few nodes in, but these are the building blocks we work with. Every Hadoop system needs a certain number of management nodes, a certain number of data nodes, and a certain number of worker nodes, and we're spending a lot of time in the division to optimize and tune these into a package that we know will work when you get it. You don't have to build it and wonder why something isn't working properly. So I'm working in these building block structures. Again, being in Houston, one of our leading universities that's adopted the Power Platform, I can actually, as a follow-up to this meeting, I'll provide the account team with some information. One of those is this LSU white paper, but basically I worked on this project, and I had a really skeptical customer in the summer of 2014, who said, Terry, I don't believe anything you're saying. We're an Intel shop. It doesn't work that way. And I finally said, Dr. Park, you'll never know if what I'm talking about is true unless you pick up the phone and call me, and we take your hardest workload and run it. Well, about a month later, I got a phone call. Said, Terry, I got handed a 3 terabyte metagenome from the Department of Energy, and they want us to use our genome assembly method to characterize this cow gut. And it's taking 30 hours on 120 nodes of our Dell cluster. If we run more nodes, there's some kind of confluence in the performance. But anyway, so I said, okay, I can do that. So we actually gave the customer our entire cluster for 1 week up in Poughkeepsie. This was not Minsky, not NVLink. It was the box of one of the boxes on the far right of my picture. We spent 3 days in a remote tuning process where the guys on the ground were logged into our system in Poughkeepsie. He copied his Java code up, his workload, but because it was a 3 terabyte data file, we actually had to FedEx a NAS array to New York and bring it back into the GPFS farm. On Thursday morning, Argo is his name. Argo, we had a team working. And Argo said, oh, we all agreed, let's go. So he fired up the whole entire job that was taking 30 hours. And I was in a meeting like this at 2 o'clock, and I got an email that said, wow, 6.25. And so what we did was through that process, we literally proved that assembly method, which ran on 120 nodes, that took 30 hours, ran on 40 nodes, taken 6.25 hours. And at that point, Dr. Park changed his whole strategy and said, we're going to move forward in our big data plan with IBM. So we're a good partner. The second thing we did in this project was that we had just come out with an HDFS connector. Part of Hadoop it's built off of lots of servers with internal disk, and everything is available and no external. Well, we made everything external, and because our servers up in Poughkeepsie only had 2 disk drives in them. And you could appreciate this, Christy, for the first 3 days we were having trouble because this workload that was producing 1 billion files in the job that were temporary 4K files was crapping out in the directory structure. But one of the smart guys up there said, I think I might be able to get around this. So we said, why don't we make one directory for each worker node and emulate what Hadoop is doing locally. So we had a directory for every server and 6 subdirectories of cache representing 1 disk under each server. And when we did that, GPFS took off and ran, and we got this number. So it talks about scalability and file system access, and so you can download it, and we published it and released it at Supercompute 15, and Dell got really mad at us. Okay, I've talked about that. I'm going to move into OpenStack a little bit. All the OpenStack platforms run on Power 8. The reason we're telling you all this stuff is because there's this great big cloud over IBM that says, we haven't heard from you for a long time. Power 8 is a foreign entity. What runs on it? Everybody's skeptical. And as I said at the beginning of the meeting, when we came out with Little Indian support of Linux, all the game changed. And now we can have real conversations and begin to have real world activity, which you become a part of. Part of that is OpenStack. And I was at Clemson University. I was talking to David about it a month ago. And Clemson has a OpenStack cloud shared system funded by the NSF. We're working with Dr. Casey Wang there to create a power branch of that and experiment with it to prove that, of what I just said, interoperability. And so Dave, where are you guys in the OpenStack deployment realm? So how okay, so I wasn't aware. All right, what's that called? Jetstream. I'll remember that. I'll look that up on my airplane ride tonight. So this is relevant to supporting that. We're very closely tied with Ubuntu. People are asking me why Ubuntu. We use Red Hat or CentOS. It's pretty simple. Ubuntu has a flexible release schedule. And as our products are rolling out, they're rolling with us. Red Hat has a very rigid release schedule, like twice a year, so we have to play catch up on a Red Hat side. But we're tightly aligned with Ubuntu. Ubuntu tells me that 60-some% of the cloud adoption on OpenStack is on Ubuntu. What's yours running on? Okay, you're doing all three. Okay. Yeah. Yeah. No, none of that. No. Okay. Should I talk about it? Is anybody here doing FPGA work? I don't want to spend a lot of time if it's not there, if there's not research. We got certain areas where this is a hot topic for institutions. It was big at Georgia Tech.
We have a lab that's doing
Yeah. I have a customer at Auburn University is my other pet project. It's in cybersecurity. And we actually have Minsky servers with NVLink GPUs, and right beside them we're putting FPGAs so that Dr. Shellham can do in-flight cyber forensics of data packets on the FPGA before it passes to the GPU, before it gets processed to the processor to determine it's a bad guy. And so that's and I'm going to skip this, except for this. The secret sauce underneath this is what's called the coherent accelerator processor interface. It's basically the same core technology that's allowing NVLink to talk to the processor coherently. And an adoption of that for the FPGA is available such that the Xilinx FPGA can see all the memory in the processor of the server. So this takes an FPGA that was limited to however much memory was on it, and it opens up to a terabyte potential of RAM. And then how does your algorithm that you have to load on your FPGA interact with that? That's a custom thing among every instance. We have some packaged versions which are taken advantage of. We have a gzip packaged version of CAPI. But for the most part, every conversation I'm having is about whoever the person is, my niche thing that's an FPGA application, and I want to know how I can now move into this and begin to take advantage of this memory, and that's what we call our CAPI developer kit. You go to Xilinx, you get an FPGA, you put it in the server, it's enabled already with this API, this, what's PSL stand for? I forgot. Bottom right-hand corner, processor service layer. That's the part that talks to the processor. And anyway, it's enabled with that, and then there's a whole development kit that comes with that helps you understand how to read and write to it. Okay, that's all I'm going to say there. The other area we're spending time is on open source databases. Ronak and others talked about it. These are the predominant open source databases we're seeing. The traditional SQL database, like Microsoft SQL and Oracle, are they would argue differently, but we're seeing them decline in the total growth. Whereas NoSQL databases are increasing in adoption. It's because of this rapid data in motion issue. I literally have seen demos of graph databases on a GPU with 5 million records being scanned in 3 milliseconds. And that one is particular for a visualization of Twitter data in a certain geography. You can zoom in on it with Kinetica, click the button, and it does a new graph. So this whole graph database area and open source database area is booming for us, and we're supporting these systems. I have a little bit of different philosophy. SAP HANA is supported on Power, but Mongo, Neo4j, Maria, Cassandra, Postgres, etc., they're all supported, they're all run, we have keen partnerships with them, and the systems are performing with blazing speed. I talked about graph databases. Key value stores is another area. The particular project we were working at LSU dealt with key value stores of all these billion data files, and that's since moved on to another database, another calculation space, I'll call it. If I was a professor and I was having to give an assignment, or what was the bonus test on a question, this would be your bonus test. What's the 3 things we wanted you to remember? 8 threads and 4 times memory and cache on our systems and Intel. Okay, let me go to storage. This should be very relevant to you guys. This is actually the picture that came off of a napkin with my customer at Baylor College of Medicine. And what we're trying to do is emulate in high-performance computing staged tiering of data at runtime. So our center of the universe for the file system in our high-performance computing strategy is spectrum scale GPFS. I'm glad to be in a room where it's a positive thing, although it's not negative everywhere else. It's just people may or may not have it. Our number one competitor in this space, in this storage space, is DDN selling GPFS. So it tells you the worth of the file system. We have created in the spinning disk world layer, we have created optimized, tuned racks of GPFS systems with native RAID implemented, and those are what's called our elastic storage server. Up until a few months ago, I'll move over here. Until a few months ago, we didn't have a flash layer. Today, we have a 128, 256, 512 terabyte flash layer that sits underneath spectrum scale. And so those 2 blue boxes on the left represent NSD servers that you're familiar with. Yeah, that's a rack of GL6 in the middle. And this is all brand new on the flash side. I have another slide that talks to this in a minute. But the concept here is that we're in a new paradigm when you implement something like LSF or a smart scheduler, that we can prefetch the data files necessary for the next job from spinning disk, bring it to the cache by virtue of its metadata location or its real location, move it into cache before the job starts. Then the computational job is running out of flash instead of spinning disk. At the end of the job, temporary files or whatever policy is invoked, and data starts moving back to multiple tiers. The spinning disk tier is in the middle. That could also be SSDs. These, I don't know what you're responding with, but SSDs in our GL platform. The next layer is object store. And we bought a company in last year called CleverSafe for on-premise and off-premise object store. So GPFS has been integrated into that so that an auto-tiering function can move to those files to the object store while maintaining the file name integrity in the file space. Lastly, to go out to the cloud, whether it's Amazon or Google or our own soft layer cloud, we have cloud object storage, or what we call transparent cloud tiering, that will move the files to an S3 destination so that the file name or the file system knows which tier it's on at all times and bring it back appropriately. Does that make any sense?
Yeah, I'm just wondering for the free punch that you mentioned, is there any
Only the fact that the key word was integration, and I don't know that those have been integrated. Yeah. Yeah. I haven't heard about it, but this guy right here is one of the experts of spectrum scale GPFS, and it's so certainly something we need to look at. You have HPSS here. I heard it was at Purdue yesterday. So if there's an integration element we need to do to help you, we should do that. But I don't know the underlying details of that. And HPSS is a whole separate family, and you know better than I. So let's take that as some kind of follow-up, and we'll have to get back to you in California. Or, I'm sorry, what's your name? Charlie, the new Christie. All right. Yeah. Yeah, okay. All right, my apologies. So this is the concept of our spectrum scale part of file migration, and spectrum scale being the center of our file universe. Since you guys are smart on spectrum scale, all I'm going to focus on is how they're packaged for you. This is a precursor to what you're going to see in your RFP, I'm guessing. I wasn't privy to it, Sean, so tell me where to stop. But over on the far right side is a full rack of storage. The 6 is relevant in that these are Power 8 servers. And because of those speed elements, that's why they're implemented here, and we can get higher performance than we did get with Intel servers. The 6 represents 3 and 3 trays, obviously 4 and then 2 as building blocks. So those are optimized and tuned for performance characteristics, and I'll stop short of saying the word guaranteed. North of 12 to 18 gigabytes per second with InfiniBand in the backside versus a little bit lower with 40 gig Ethernet in the back between them. We just came out with the flash layer, which is on the left, 1 and 2 building blocks, and I'm not sure how far that's going to go in upward size scale. Since you guys are keen on GPFS, I'm not going to spend much time here. You know, so with your DDN, you don't get to take advantage of native RAID, right? Because they got their RAID they're running, right?
It's just standard RAID.
Yeah. So one of our big things is native RAID and the rebuild time, and a smart guy like Stieg can give you all the details of that, but that's out of context here since we're under the RFP. But that's a really important factor about our part, and hopefully it was responded to appropriately. Right. Well, yeah. Let's see. Now I'm moving into the area of the scheduler. And there's 3 components here. One is LSF, the load sharing facility. So I'll simply put that in the space of Moab and Torque, but in terms of automated resource-aware scheduling, but being integrated with GPFS. And the second layer of this is Symphony and Conductor, and this is the guy that was asking me about Hadoop and Spark. He left the room. But this is where we have the core components are able to create Hadoop and Spark jobs on top of LSF. Is that on top the correct word?
Yeah.
Yeah.
It can be either way.
Yeah. And I don't have a lot of slides. This is a new developing area where coming out of software development for Hadoop and Spark integration. I'm going to talk about LSF. So you saw this slide from Jane. Our goal is to do what I call make the LA freeway maximum speed, maximum efficiency, no gaps in cars. And so with LSF, we're able to do forward looking and things like prefetching I talked about. And therefore, this resource-aware scheduling makes efficiency. If you're a casual type of HPC environment and the total length of the runtime is not a giant thing, then maybe this is not, important thing for you. But when you're a genome science center for profit, and it takes hours to run jobs, to process, to do genome assembly, and every minute equals $1 or some currency metric, then this is important. And so it depends on which area you're coming from. LSF, the Spectrum LSF family has about 6 components. There's a license scheduling module, which I don't, is what? Yeah, you're right. The major areas are the process manager and the application center and LSF itself. So in process manager, I'm evangelizing about the graphical user interface, the workflow modeling. How does that change the way we're doing things? I'm hearing a lot from university, department leaders or professors that we've got a lot of psychologists and biologists who are not command line savvy. So, but a computer scientist person would be. So to extend your HPC environment into the user community, you really need to have a user interface that speaks their language, which is like this. Second part is application center, which is managing all the jobs. Then there's an analytics element, which involves real-time monitoring, both at the whole cluster level and at the user level. And everything I'm talking about here runs hybrid across both Intel and Power systems heterogeneously. The OpenStack connector is brand new. The Spark connector and Docker connectors are brand new. But all of these things are integrated now as opposed to not integrated. It's all about increasing productivity. Let's see. I'll give you some more detailed design screenshots, if you will. So these are a web interface for administrators to allow you to keep track of all the jobs running, understand efficiency and workflow, what's running, what's not, yes. One of the challenges here is they don't have it, so they have the other two. So where I'm going to head with this is the academic initiative to start using it for free, right? So then there's an end user element of LSF with real-time monitoring, so a particular user can tell where his jobs are and how much he's consuming. An individual user might not care about everybody else, but the administrator does. And so these graphical interfaces help you to get a handle on this. the workflow and flow management is a big thing. I made a couple of references to what some of the customers are doing, and especially in the hybrid cloud model. This whole if-then-else construct of jobs as a graphical interface is catching on. And as I said, LSU decided to adopt this workflow interface as their teaching mechanism because it appeals to the millennial crowd, which is most of their students. Yes, in the back. Good question. I've been different. Yeah, so let me go back to the mic here. The question from the gentleman is, does LSF require that everything be LSF-ish? And the answer is yes. So I'm trying to work with Stig's colleagues to create some integration with the other guys.
So the answer is yes.
Okay?
So I apologize.
There you go.
The real answer, if I'm allowed to.
That you can do that. Come talk. Here, Stig, right here. Take this one.
As with most things in the architectural point of view, it really, it depends on your use case. So, is LSF tightly integrated with the family of products that sit around it? And is that, if that happens to be your environment, is that an optimal configuration? Of course. If in fact you have remote schedulers involved, are there protocols that inter-scheduler protocols that LSF supports, like Drama, and maybe you're doing some stuff here and you're doing some stuff there, and the two can exchange via that protocol, then that's also supported. Yesterday we had a big discussion about there's an effort by some of the research scientists for a common workflow language, which is kind of a meta scheduler on top, and the ability to describe these research jobs and give it a container and a set of libraries and a data set so that the notion of your research can be reproduced by somebody else in another environment when the underlying OS and the underlying, well, it's running in a Docker container, but the underlying processing architecture and how that is scheduled and the nuances about that would be just described, but still allow you to run in those things. So LSF does support those different interfaces. Does it mean you're going to get a turnkey? It depends, right?
Yeah, so
long story.
In the spirit of what I've been trying to create as a theme of partnership and places to do that, because you guys are keen on spectrum scale GPFS, and as I'm about to show you, LSF is now free in our academic initiative, you're in a key place where you could be the guys that help us create this integration he's talking about or perfect it, right? And because you have the pieces of the puzzle necessary to do that where others may not. And that's this protocol translator stuff, for lack of a better words. So yes and no. Did we answer you? Is that good? Yeah. It all depends. Sometimes it's a good answer, sometimes it's not. And I think I've talked about this a lot. The relative fanciness of the workflow modeler, and it all depends on where you're sitting. Let's see. I'm going to provide all these slides to our contact, probably Eric, to get to you guys, and they'll be in PDF format. This data manager, by the way, Christy, is the prefetcher, okay? And it's the mechanism to get that done. LSF also has the ability of job scheduler of jobs, scheduler of schedulers, sorry. So how far you get this nested, that remains into how you implement your systems. Okay, let me talk about that. I've been preaching it. So up until Supercompute 15, we have been having a a challenge with customers in the university space who said LSF is great, but we can't afford to spend money that's big money like a Ford or a GM or some commercial entity would do for a valuable product when we got Moab and Slurm and Torque, 3 that are free. So until you can overcome that, we can't really adopt it. Well, that message was heard, and at Supercompute 16, we announced the adoption of the whole LSF family into what we call the Academic Initiative. This is a bigger, broader thing within the IBM company. There was a guy talking about statistics, but SPSS is a software package in the Academic Initiative, download, website, contract thing. And so these are there. And let me explain what we built, and you can tell me whether this is good or bad. So there's 3 flavors of this. One, you register to be a user. It's a self-auditing process. The first requirement is that you got to be an EDU entity. Second requirement is that the totally free version has no limits, all the software, but you don't get any help from us. It's community support, and there's no maintenance on it. So next rev of the software, we're not going to flow it to you. You got to keep up with it, and so it's a manual process. And in a place where a customer might be not a savvy user, that might be a problem. But in a place like here where you are, I'm going to call it savvy, that might be okay. I don't know. One thing I've asked the team to look into, you didn't hear this, is that we need some kind of starter book that says, okay, you're going to be a self-support user. Here's how you get started so you're not floundering at the first day. The second way we did this is if you have, and the requirement is they cannot be commercially funded projects, which is why I was asking. Many institutions have Boeing or Ford or whoever funding their projects, and if that high-performance computing job is being run under LSF, that would breach this concept. But for research and teaching, totally perfect. So we have to kind of differentiate that, and you get to determine it. For commercial use pricing, for example, I was at Georgia Tech. They're funded heavily by commercial institutions, lots of projects. So it's way the other side of the equation, less teaching, more. Georgia Tech Research Institute, sorry. And they're way heavily funded by commercial. So therefore, how can we make it available to them? So the offering team came up with 15% cost. That also includes support and maintenance, and you can call IBM and guys like Stieg to get help and help you perfect the system. A blended solution would be you get to determine how much of your cluster work is being done for commercial purposes and how much is research. You get to determine that, and part of it's then free, and the rest of it is 70% off. So that's what we've come up with. We'll see how that plays out over the coming years and months. But you're in a place where I have high confidence here that you could adopt LSF and begin to see how it gets integrated with GPFS and what's that going to do for you in your environment in the free version. And it behooves us to spend a little time with you to help you get there, even if it's the free version. So that's a subject we could take up, that Sean and his team could take up and figure out what the right answer is. That's collaboration and partnership. You download everything from this website. You have to log on. It's professor-based, and it's developer.ibm.com, academic program details. And once you're there, on a yearly basis, you re-up your username. And each professor can give subordinate rights to their students for use of the products. Okay, so it is right on time. So, I got one more. I got to get through this here. Let's see. got some things out of place. I'm going to have to reorder these. There we go. Do I need to, you guys are Mellanox gurus. Would that be a fair statement? You know, okay. What about the cluster side? Okay. Well, let me go there. I have a short slide deck Mellanox gave me. I'm not the right guy to give the talk, but I'll give you the flavor of it. Where'd it go? There we go. So we've embedded all of the Mellanox platform into our cluster offering. So these are SKUs on IBM that we ship with the products. The standard InfiniBand card in a power server is going to be a Mellanox card, whether it's EDR or actually the new ones are EDR that can backscale to FDR. The switches are Mellanox EDR switches. We also have adopted their Ethernet switching as well for 10 and 40 gig. And there's a brand new offering under Mellanox just for us for a 1 gig switch. So you'll see their adapters, NICs, switches, all that stuff as part of our delivered offering. Doesn't mean you can't do that, just means that as a common shipped thing from IBM, that's what we're bringing. We're also going to be right in line with them as the new high-speed networks come out from Mellanox. They will be embedded into our power server structure. On the back side of our storage, you can choose InfiniBand or Ethernet, whether it's 10 or 40 gig Ethernet. Basically, these are the switches. And I don't know what you have in your data center. And of course, if you had Ethernet, we eliminate that from the component mix and adopt whatever you have in a cluster design. Last topic. A lot of universities are on a couple of different scales. Really savvy, and those that are less savvy in terms of HPC, so smaller universities. So what we do is we take a total solution concept about it, and what I try to do is make sure that I'm delivering you an integrated rack, wired and cabled, operating. We plug in the power cord into the PDU, into the power source, and the cluster comes up running, whether it is one rack or 10 racks or 50 racks. There's a cost associated with that, and some universities want to say, okay, just deliver all the stuff to us and we'll build it. Or what we're going to do with, I think Virginia Tech, put these racks in and we're going to come to